going to look at a couple of properties of the so-called hat matrix, which we've said is this matrix here, X transpose X inverse X transpose. We have a little look at the order of this matrix. This is n by p, this is p by n, this is n by p, and of course X transpose is p by n. So this is an n by n matrix, and the first thing we want to look at is what's the transpose of this matrix. So we're trying to transpose the term X transpose X, X transpose all transpose, and we can use the rule that the transpose of a product is the product of the transpose's reverse. In other words, if we call this matrix A, this matrix B, and this matrix C, what we're looking for when we transpose it, if H is made up of A, B, and C, then if we transpose this, what we're looking for is C transpose B transpose A transpose. So we use that rule to find the transpose of this matrix. What we have to do, this is C, so we take this down and transpose it. So X transpose transposed is X. This term comes down here, so this will be X transpose X inverse, and we should transpose that, but we can check if you want, that's a symmetric matrix, so that is its transpose, and then finally this term comes here and is transposed, so that gives us that transpose is X, XTX inverse XT, and of course that's the hat matrix. So, provided you're happy to check that this is indeed a symmetric matrix, we've just seen that the hat matrix is a symmetric matrix. Now the next property of the hat matrix we're interested in is that it's a symmetric, an idempotent matrix. So in other words, hat squared equals the hat matrix. We've just shown that it was symmetric. And if we want to see this, well, we can just write it out in full. X transpose X inverse, X transpose, and then we multiply that by X transpose X transpose, and I think one of the key ideas here is that you would expect, if you were multiplying matrices, that one was transposed relative to the other to form the cross product, but of course this is a symmetric matrix, so we can write it like this, and it's very simple to see what's going on here. We have X transpose X inverse multiplied by X transpose X, so of course this reduces to X multiplied by an identity matrix multiplied by X transpose X inverse multiplied by X transpose, and of course anything multiplied by an identity matrix gives you itself back, so X transpose X inverse X transpose. So the hat squared equals the hat matrix. It's an idempotent matrix. So perhaps the last thing that's worth exploring with the hat matrix is the trace. So this is the sum of the diagonal elements of this matrix. There's an easy way to do this. If we use a rule where it's possible to do this, if we had two matrices A and B, and it was possible to form the matrix BA, these would have the same trace. Not often we can do that with many matrices. In this case we have square and symmetric matrix, so there's no problem in doing this. So the hat matrix is x, t, x inverse, x, x transpose, and if we call some part of this A and some part of this B, then what we're saying is that the trace of this matrix is equal to the trace of x transpose x, x transpose x inverse. Now that we can see instantly reduces to an identity matrix. So all we need to know is the order of that identity matrix, and we know its trace. Well, we said that in our notation x was an n by p matrix, so x transpose is p by n, x is n by p, and this is p by n, and this is n by p. So this identity matrix here that we've formed is a p by p identity matrix. So the trace of an identity matrix that is of order p by p is equal to p. Therefore, we know that the trace of our hat matrix is also equal to p. So we've seen three properties of the hat matrix. We've defined a hat matrix equal to x, x transpose x inverse, x transpose. We've said in our notation x has n rows and p columns, and we've seen that h is symmetric. We've seen that h is idempotent, and we've seen that the trace of a hat matrix formed from matrices of order n by p as shown is equal to